Okay, start the next session. Just a quick introduction to myself. My name is Stephen Wells, and I'm a fellow working at the Storage Research and Design Center for KIOXIA in Folsom, California. And this slide presentation is a mouthful, but this is about some optimizations that we took on to data center, our Dataset Management Deallocate. That the OCP SSD spec allowed us to improve upon compared to what we couldn't do without the OCP spec support. So quick introduction of myself. I've been involved in storage now for over 30 years. I've been in multiple generations of SSD design and have been working on a product for KIOXIA that I'll describe here in a second called XD6. And as a reminder, feel free to come by our booth and see some of the demos that we have around it. So real quick, if you look at the NVMe spec around deallocate, and if you guys don't know what the deallocate command is, there's no reason to be attempting garbage collection on data that the host no longer needs. And the host may not have rewritten the data, so they can just issue this command called deallocate, or TRIM is the old name, or the common name that's been commonly used in that. And it allows you to relieve some of the activities around garbage collection, which reduces the wear and whatnot. So NVMe had a very light set of requirements around it. And the light requirements were, one is dataset management was a hint. So you could literally just blow off the dataset management commands if you were so inclined. But the only requirement that they did put in place is what I have highlighted here, which is if you read a value, it needs to be deterministic. Or if you trim a value, it needs to be deterministic on the readback. Well, there's an interesting optimization that you can take on. So let me describe a little bit. There's much more guidance in the OCP spec, and I want to give a call out to the metadata folks that made the contribution to the OCP spec around this, but gave some better guidance in this. And the first one I'll talk about is around the determinism. What it says in the OCP spec is it needs to read zeros, ones, or prior data. Does not have a requirement around deterministic behavior. And we're going to take advantage of that in an optimization we'll show you guys in a second that we did on XD6. A couple other things that were in there was they add some requirements that deallocate is there for performance and reliability benefits in the over-provisioned space. It's left unspoken in the NVMe spec, and it's because of that guidance. It's well, I don't have to. I can just blow off the command. And the other piece of guidance that they gave was around that device shall support garbage collection during periods of no I/O. So a background garbage collector, and then we're going to talk about a background trim as part of the background garbage collector, allows us some performance optimizations that you wouldn't take on. And whether this should or shouldn't be done was up for debate. And it was really nice that the OCP contribution made around this, made it clear exactly how the direction these drives should be implemented. And then finally, and I only gave one small summary of this thing here, the OCP SSD spec also gave guidance around what trim performance and bandwidth is. And I'd be curious if anybody else knows anything after the session and wants to hit me up on this, but I am unaware of any industry standard anything around what the trim performance needs or should be. And this gave some guidance in here. Hold on to this one. A 3 GB trim should do about 500 gigabytes a second of trim bandwidth at a P99 latency of 10 milliseconds. And so it was really nice to have that guidance, to have that direction, and also, as you'll see in a minute, that relaxation of the deterministic requirement that we took advantage of in the design that I worked on. I'll take questions at the end. So the project that I'm going to talk about that implemented this and took advantage of this is KIOXIA's first product in this space, our XD6 family of products. It's our 4th generation SoC controller. It's a Gen 4 PCIe x 4 device with TLC memory. It's pretty much targeted directly at the hyperscalers. We have a EDSF E1S 9.5 and 25 millimeter solution available. 2, 4, and 8 terabytes at 12, 14, and 20 watt power targets respectively. NVMe 1.3c base compliant, and then OCP NVMe cloud specification conformant. MI, and also included a feature that was published in a later version spec called the latency monitoring feature. So it's an independent original controller that KIOXIA designed, as well as the firmware internally, optimized for read-intensive applications, and then conformant to the OCP specification, truly focusing on quality of service, reliability, and then robust TCG security support as well. So a little bit about the implementation that we picked inside of internally. So you can specify in a single trim command an extraordinary amount of LBA space, and to process that list can take quite some time. The way we addressed that was with a two-level lookup table architecture. So the classical 4K FTL that is known and loved by most people was, which is what we literally call our level 2 table. We now had a level 1 table. And our level 1 table included something called a deallocate flag bitmap. So literally, it was 2 bits of data for every 256K of LBA space, which wasn't a lot of memory, about 4 megabytes of memory on a 4-tib drive. But ultimately what that allowed us to do is we could flip a bit or two and deallocate 256K of trim data without having to go into all of the 4K FTL table entries. So the deallocate command was automation ingressed into the SoC. The range list was processed using hardware automation and updated this deallocate flag bitmap. And really only thing is if we had any deallocate lists that didn't align to 256K, we would have to go into the level 2 table and update the 4Ks, and then we could issue command complete quickly. Now what would happen then is, 2 things would happen after that. One is any reads or writes that would occur after that, before the trims are fully processed. The hardware managed the cache coherency. So you had this ability, once you recognized it was in the first level table, the hardware would properly return it as trim data. And the second thing is if writes came in or whatnot, it would recognize, oh, this is writes on trim data, and would manage something correctly. And then finally, we would process this level 1 table into the level 2 table, pretty much when we had any idle core processing time internally. So we would just take the level 1 DFBs, process them into the level 2 table kind of at our leisure when we had some idle time. And then other accounting such as block counts required for namespace utilization and whatnot would get processed as a background event during these idle times. So ultimately what this allowed us to do with our high degree of automation, it allowed us fast command completion as well as had the coherency that we were looking for. We ran into an interesting case after all of this, and this is where OCP came in an interesting way. In fact, there is one of the OCP tests called IO-Go would machine gun random trims against random writes and random reads. And every once in a while you would run into an interesting case where a write was now buffered. We had committed that write, but it was buffered and it hadn't been written to the NAND flash memory yet. It was just stored in the buffers. And then a trim would immediately come in. Well, we hadn't updated, we don't update our 4K lookup table until we've actually committed it to the NAND. We didn't want to process the trim, so we would actually stall the trim on a buffered write. And this would increase the trim command latencies. And so then if a read happened to come in, we would actually stall the read, and then we return zeros in a deterministic way. We experimented with and had a discussion with the hyperscalers, and they said, our spec supports this, is if we do recognize that we have a buffered write command, rather than just stalling the trim, we actually just drop the trims on the conflicting writes. It's a trivial amount of writes, it's a small number of writes, but rather than stalling the trims, we effectively drop them out of the 256K table and out of potentially the 4K table. And because our controller had cache coherency monitoring on this, it would return, and it allowed us, by the way, the fast command completion. But our controller, because these were outstanding buffered writes, it would read zeros back. But since we ultimately discarded the trim for a fast response latency, it would then return prior data after the controller had finished its job. So it followed every OCP rule. It was 1s, 0s, or prior data. It wasn't deterministic. It would return 0s because of hardware automation, followed by returning prior data. But this allowed us to have a trim optimization that gave us a trim faster completion time. And this was only made possible because of this case. So the pathological test was write trim, read, 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 read. And yes, it's a very pathological case, but even in the pathological case, we have excellent trim times. I see you shaking your head. I'd love to talk to you some more about that later. Give you an example of what this is. Within OCP, there's this trim target test that I mentioned before. And here's the XD6 measured trim performance, and this is against a common competitor drive that's also claiming OCP compliance here. And so looking specifically, 64 megabyte trim was expecting 50 gigabytes a second. Competitor did well at 214, but we was clearly faster in that. Trim latency's 10 milliseconds, we were 300 microseconds. The more interesting one is down into the 3 gigabyte trim. The requirement was 500 gigabytes per second. We have the number kind of blows my mind, and I have to check the zeros every once in a while. It's about 22 terabytes per second of trim bandwidth. And given the situation that we had 5 years ago, having that kind of trim bandwidth available to us is pretty spectacular, to say the least. And for the 22 terabytes of trim bandwidth, we could have a command latency of 400 microseconds. And then compare that to either a competitor drive or the specification. We exceeded that pretty spectacularly. I'm pretty happy with this. So just to summarize this, OCP was, and we wanted to give a really good kudos to the Meta team and OCP for giving this guidance. OCP is the only standards body or industry body that I'm aware of that offers any deallocate performance. And from the stories I'd heard from some of the hyperscalers a few years ago, trim performance varied wildly, and for the most part, the trim command latencies were just really, really unacceptable and rejected on a regular basis. I think the KIOXIA team heard that and went with a very aggressive approach on trim. And then they also offered some standardized workloads around trim and trim performance, which I thought was pretty spectacular. And then finally, the Datacenter enabled XD6 drive that KIOXIA is offering on the order of 20 terabyte per second trim bandwidth and latencies, well under 500 microseconds at P99. And so maybe the question finally is nothing more is what's the value of the trim in real workloads? I think that's an interesting conversation that I'd like to have some industry time spent on to get us some better trim metric workloads that we could all work from. But in general, I just wanted to give a good kudos to the OCP team for providing really the only guidance in the industry around what the deallocate performance needs to be. And that's all I had, and I open it up for a couple minutes of questions. Did you want to?
NVMe says that you have to report whether you do 1s, 0s in there. So
that's correct.
Even though it says you have to be deterministic, you still report the value, which actually matches OCP.
So let me repeat the question because I know it's being recorded and they can't hear you. So your comment was that NVMe asks you to declare whether you return 1s or 0s. And the NVMe spec also declares it being deterministic. And you're saying that is the same as the OCP spec.
So I'm saying if you return 0s in one read and non-zero in another read,
It's interesting because the contributor of those specifications did not agree with that. And it might be good to have a conversation with the guys at Meta that contributed that requirement. The requirement is shall return 0s, 1s, or unchanged on a sector by sector basis, does not use the word deterministic. And they said that was with intent is why that it was done that way. And that allowed that non-deterministic behavior. So that is the optimization that allowed us to reduce our trim latency bandwidth. So did that address the first part of your question? Anything else anybody has? All right, it says I'm at 0 time. Thank you very much, and you please hit me up afterwards. Thank you.